All right, let's talk about something that feels like actual magic. How in the world does your computer run a web browser with 50 tabs, your music, a game, and who knows what else, all at the same time, without just bursting into flames?
You know the feeling, right? You're totally in the zone, everything's flowing, and then suddenly, it's like you're moving through molasses. The mouse stutters, a click takes an eternity. It feels completely random, but it's not. What's actually happening inside that box is a really fascinating, high-stakes drama.
So, to pull back the curtain, we're going to use a simple analogy. Think of your computer's operating system, your Windows or Mac OS, as a super smart but totally overworked librarian. The RAM, or memory, is the librarian's desk. It's not very big, but it's where all the immediate work happens, and it's incredibly fast. And your hard drive, that's the Grand Archive, this colossal library that holds every single program and file you own. And right away, you can see the problem our poor librarian is up against. The desk, your RAM, is tiny. It can only hold a handful of books at a time. But you, the user, you want access to everything in that Grand Archive, and you probably want it all now. So, how does the librarian even begin to manage that? Well, it all starts with a little bit of translation. See, when one of your programs needs a piece of information, it thinks in its own little world. It asks for, say, page 256. We can call that its logical address. But the librarian knows that page 256 isn't just floating around, it's sitting in a very specific, very real spot on the desk. That's the physical address. The librarian's core job is to instantly translate "I need page 256" into "Oh, that's right over here on the desk." Now, to keep everything from becoming a huge, messy pile on the desk, the librarian needs a system. And the first really brilliant idea they come up with is something called paging. It's a system designed to bring some serious order to that chaotic workspace. The idea behind paging is actually pretty simple. Instead of trying to haul a giant, heavy book onto the desk, the librarian breaks the book up into small, equal-sized pages. And the desk itself, it's divided into perfectly matching slots, or frames. This way, pieces from a whole bunch of different books can sit neatly on the desk at the very same time. So how does the librarian find anything in this system? With a trusty set of index cards, of course. In the computer world, we call this the page table. So your program asks for a page. The librarian glances at the index card, and that card tells them exactly which frame on the desk that page is in. It's an unbelievably fast lookup, and poof, you get your data pretty much instantly. And this system works beautifully, right up until the moment it doesn't. I mean, the index cards are perfect, the pages are all neat and tidy, but the desk is still just a desk. It's finite. So what happens when every single frame is full, and you ask for a page from a book that isn't even on the desk yet? Where is it supposed to go? This is where the real magic has to happen. Okay, to solve this problem of a desk that's just too small, the librarian pulls off this incredible illusion. It's a trick that is so fundamental, it powers almost every single modern computer. It's called virtual memory. And it's all about making you and your programs believe that the desk is infinitely large. So here's how the trick works. The operating system, our librarian, starts using that massive but slow Grand Archive as a sort of overflow area for the small, fast desk. It basically lies to every program and says, hey, don't you worry, you've got all the space in the world. It creates this illusion of an infinite workspace by constantly juggling just the most important pages onto the physical desk. And the secret behind this whole magic act is a beautifully simple idea called demand paging. The librarian is, well, kind of lazy in the best way possible. They don't waste any time bringing pages to the desk that you might need later. They wait until the very last nanosecond, until your program is screaming, I need page 72 right now. Only then do they go and get it. It's incredibly efficient. But, and you knew there was a but, there's a catch. That specific moment when a program asks for a page and the librarian has that, realization that it's not on the desk, that moment has a name. It's called a page fault. This is the critical point where the super fast workflow hits a wall. Everything stops, and the librarian has to literally run all the way back to the Grand Archive to find that page and bring it back to the desk. And the cost of that trip to the archive is just mind-boggling. Seriously, look at this. Getting data that's already on the desk, in RAM, takes nanoseconds. That's billionths of a second. But when a page fault happens, bam, the whole process stops.
The trip to the hard drive and back takes milliseconds. That's a million times slower. To put that in human terms, it's like you ask someone a question and they have to stop, leave the country for a week, and then come back to give you the answer. It's a huge delay. And this brings us to the dark side of this magic trick. What happens when it all goes horribly, horribly wrong? What if the librarian is forced to run to the archive for every single thing you ask for? Well, that leads to a catastrophic state, a total system meltdown, known as thrashing. Thrashing is just pure chaos. Imagine this. You need page A. To make room, the librarian grabs it from the archive and puts page B back. But the very next thing you ask for is page B. So the librarian runs back, gets B, and puts page A away. Then you need A again. The librarian is now spending 100% of their time just running back and forth, swapping pages, and 0% of their time actually helping you get any work done. The entire system just grinds to a halt. This chart shows you exactly what that looks like. As you open more programs, your computer's productive work goes up and hits a nice sweet spot. But look what happens when you add just one too many things. Performance doesn't just dip a little bit. It falls off a cliff. The system starts thrashing, the CPU is spending all its time swapping, and the amount of actual work getting done plummets to basically zero. That's the freeze. That's the stuttering you feel. So all of this means that even that trip to the archive has to be as fast and smart as possible, right? So how does our librarian decide which book to grab next when a dozen different requests come in at the same time for books all over the library? Well, they've got a few different strategies. They could do first come, first served, which sounds fair, but it's really inefficient. They could do shortest seek time first, grabbing the closest book, which is fast, but might mean a request for a book way at the back of the library gets ignored forever. A much better approach is the scan algorithm. It works just like an elevator. The librarian just sweeps from one end of the archive to the other, picking up all the requested books along the way. So let's just quickly recap this whole incredible dance that's happening inside your machine. Your RAM is the small, fast disk. Paging is the index card system that keeps it organized. Virtual memory is the grand illusion of an infinite disk, which depends on these really costly trips to the hard drive called page faults. And when there are way too many of those trips, the system collapses into that horrible state we call thrashing. So the next time your computer starts to slow down and everything freezes up, you'll actually know what's happening. It isn't random. It's that clever librarian inside your machine, running frantically between the desk and the archive, desperately trying to keep up with every single thing you're asking it to do. You're not just waiting for a slow computer. You're witnessing a brilliant system being pushed to its absolute limit.